Okay, so we're going to continue with the last section, or the last part of section 3, looking at how to calculate Ka and titration of a weak base with a strong acid. Alright, so we've been talking about how to use the Ka and calculate all these pHs. Now let's kind of go the opposite direction. So we have 2 millimoles of a solid weak monoprotic acid, and we're dissolving it in 100 milliliters of water, and then we're titrating it with 0.05 molar NaOH, and after 20 milliliters of NaOH, the pH is 6, and so we want to find the Ka. Alright, well, we need to do a stoichiometry problem first, and so we're going to use Ha to represent our acid, OH is our base from the NaOH, and then we've got our conjugate base and our water. So before the reaction, and let's see, we had 2 millimoles, it said, of the HA, and for the NaOH we had 20 milliliters of 0.05 molar, and so that gives me 1 millimole. We don't have any of this, and we're not including water, so here, because everything's 1 to 1, we can subtract 1 and add 1, and so this gives us an after reaction of 1 millimole of acid, no OH minus, and 1 millimole of our conjugate base. So that's our stoichiometry part first. Because it's a weak acid, we've got to do both parts. Now we go to the equilibrium part. Well, after the reaction, we've reacted all the OH minus, so our species are the acid, the conjugate base, the Na plus, and the water. And so we know that Na plus isn't going to respond at all, and so we're basically going to take our acid and go to H plus and A minus, or our conjugate base. So we have our ICE table. Well, we had 1 millimole of the acid, but we need to also incorporate the total volume. So we had 100 milliliters of water plus the 20 milliliters of the base. So this is 1 millimole over 120 milliliters. And so that should give us 8.33 times 10 to the negative 3 molar. Our H plus is initially 0, and our A minus was also 1 millimole divided by the 120 milliliters, so this will be 8.33 times 10 to the negative 3 as well. So remember these values, the 1 millimoles coming from the stoichiometry part of the problem. So we have minus x plus x plus x, and so we have 8.33 times 10 to the negative third minus x, x, and 8.33 times 10 to the negative third plus x. And so we can put this into our Ka, which is equal to our H plus over our A minus over our acid. And did it give? No, we're finding the Ka. That's our issue. Okay, so our H plus is x. Our A minus is our 8.33 times 10 to the negative third plus x. And our HA is our 8.33 times 10 to the negative third minus x. Well, we know what x is, because x represents H plus. We know that the pH is equal to 6, and so we can do the anti-log or the negative log of 6 to go backwards and get the H plus. And so if we do that, anti-log of, what, 6, right? Yeah. Then that's going to give us 1 times 10 to the negative 6th molarity, and so that's our x value, so now we'll plug that in. So 1 times 10 to the negative 6, 8.33 times 10 to the negative 3, plus 1 times 10 to the negative 6, divided by 8.33 times 10 to the negative 3, minus 1 times 10 to the negative 6. Okay, and if you do all of that, if you'll note, you should get 1 times 10 to the negative 6. Okay, and so as our Ka value. So hopefully what you're noticing here is that the Ka is equal to the H plus concentration, and we had a situation where that was the case when we did the weak acid strong base titrations. So an alternate way to look at Ka, the original solution contained 2 millimoles of the acid. When we did the stoichiometry part, we ended up with 1 millimole of acid and 1 millimole of the conjugate base because of the amount of the NaOH. And so if you remember from the previous section when we had the situation where the concentration of the acid and the conjugate base were equal, this was halfway to the equivalence point, or basically the halfway point. And at that halfway point, the concentration of the H plus was equal to Ka. So if you recognized that right away when you were solving this problem, you could have just said, oh, this is halfway to the equivalence point, and H plus is equal to Ka, and since you know H plus, you know the Ka value. But again, this would only work if it was at the halfway point. So keep that in mind as something to recognize. It'll make your work a lot easier. All right, so the last type of titration we're going to look at is weak base, strong acid. Whenever you're doing a titration, you want to think about the major species in solution. And does the reaction run to completion? And we've kind of had that so far. So you need to do your stoichiometric calculation to determine this. And then you choose your dominant equilibrium and then calculate the pH. So what we've been doing before, or up till now. So let's say that we titrate 100 milliliters of 0.05 molar ammonia with 0.1 molar hydrochloric acid. All right, we're going to look at before the addition of hydrochloric acid. Our major species are the ammonia and water. Ammonia wants protons from H2O. It's a weak base. And so because it's a weak base, though, it can't readily take protons from water. Remember, if it was a strong base, it'd be no problem. And so this means that our reactions aren't going to go to completion. So we need to find the equilibrium, the dominant equilibrium that controls pH, and that involves the ammonia with water producing ammonium and OH minus ions. Because ammonia is a weak base, we need to use the Kb value to calculate the OH minus. And even though we also have water here that could produce OH minus ions, we're going to go with the ammonia because it produces more OH minus in the reaction than the autoionization of water, which basically means water splitting up into its ions. Okay, so if we look at before the equivalence point, the major species before the reaction are ammonia, our H+, our Cl-, because we're reacting it with the hydrochloric acid, and water. And so we take our ammonia plus the H+, producing ammonium, and this one goes to completion. So now if we look at the major species after the reaction, so we've reacted all the H+, okay, then we have ammonia left, ammonium left, our Cl- ion from the hydrochloric acid, and water. And so if we look at what's going to actually participate, we have our ammonium going to ammonia and H+, or there's another reaction we could write. We could take the ammonia plus water, producing ammonium and the OH minus ion. So at the equivalence point, we've got all the ammonia converted to the ammonium ion. And so our major species are the ammonium ion, the Cl- from the hydrochloric acid, and the water. No reactions are going to occur here that would go to completion. And so we need to find the dominant equilibrium. Well, this is the dissociation of the ammonium ion. And so because it's an acid, we need to find the Ka, and this is equal to the Kw or the Kb for our weak base ammonia. Okay, now if we go beyond the equivalence point, because we're titrating with a strong acid, we're going to now have excess H+. Whereas before, we were titrating with a strong base all the time. After the equivalence point, we had OH minus left. Now we're going to have excess H+ left. So our major species involve the H+, the NH4+, because all the NH3 has been reacted, the Cl- and water. So the NH4+ will dissociate, but it's a weak acid. And so our H+ concentration is going to be based on that excess hydrochloric acid. And so, just like before, to find the concentration of H+, we're going to take the millimoles of the H+ that's in excess, and this is from doing your equilibrium, divided by the milliliters of solution total. Whoops. And so if you take a look at the titration curve for this type of titration, we have a rapid fall of the pH to start with, but then the rate kind of slows down, and then we get to our equivalence point. Okay, and it looks like it's less than 7, which makes sense since we are titrating with a strong acid. Alright, so that finishes up this section on titration curves. It's a little long and complicated, but if you notice, a lot of the calculations kind of repeat each other. So again, it's really important to pick out your major species. Okay, and if you have questions, we'll discuss it in class. Have a good day.